Okay, good morning. Today we're going to talk about applications of exponential growth and decay. And I just want to remind you, an exponential function has the form y is equal to a times b to the power of x, where a is a coefficient, and that indicates your y-intercept, and b is the base. When we have growth, a growth function, exponential growth function, b will be greater than 1. When we have an exponential decay function, then b will be less than 1 but greater than 0. So it'll be a fraction or a decimal. And so we're just going to hop right into examples for this. So we have example 1. A quantity of water contains 500 grams of pollutants. Each time the water passes through a filter, 12% of the pollutants are removed. So what we have here is we've got filters. So we're going to, we'll probably end up with a function, or we'll end up with an exponential function where on our x-axis it will be the number of the filter. And on the y-axis, it will be the quantity remaining. So if we think about that, if we start with, what we start with is what we have when there are 0 filters, right? So when there's 0 filters, when it hasn't gone through any filters, then that y-intercept up there is going to be that initial amount, that 500 grams of pollutants. Each time the water passes through a filter, 12% are removed. Okay. So part A, if the mass of pollutants is an exponential function, state the base of the function. Now, if we want to be graphing the quantity remaining, okay, this quantity remaining, then what we want is that base has to be the percentage of water, the percentage of pollutants that's remaining after each filter. 12% is a percentage taken out. So to find the percentage remaining, we're going to take 100% and subtract off 12%. And that gives you 88%. But we need that because this is decay, right? Because the amount of pollutants are going to is going to go down each time. Then that base, or the value b, it needs to be a decimal between 0 and 1. So we write our percent as a decimal by dividing it by 100. So that means the base is going to be 0.88. And that's what our base is equal to. For part B, in this case, the exponential function y equals a times b to the power of x, modeling the scenario, can be written in the form m is equal to a times some base b to the power of t, where in this case t would be the number of filters. So we know t is the number of filters. We've already determined that the base is 0.88, and a will be the amount, the initial amount. It's another way of thinking about that, the initial amount, which in this case is 500 grams. So then our exponential function, m is equal to a times b to the power of t, will become m is equal to 500 times 0.88 to the power of t. So with that function, we can do different things. We can figure out the amount of pollutants remaining after a certain number of filters, after it's passed through a certain number of filters. We can figure out, if we know the amount remaining, we can then solve for the amount of the number of filters that it's gone through. So part C, determine to the nearest gram the mass of the pollutants remaining after the water has passed through 4 filters. So we just want to go m is equal to 500 times 0.88 to the power of 4. Okay? And then what you want to do is remember on your calculator to do this portion first. Okay? So what we should get there when we calculate that is 299.85. So 299.85 grams. So to the nearest gram. So if we have 299.85, then what that's actually going to be is 300 grams to the nearest gram. Remember to do your, like I said here, to do the 0.88 to the power of 4, then multiply by 500. You can't combine them together to start with. Okay, so that's pretty simple, that substitution. That's just straight plugging into your calculator and figuring out the answer. But of course we know we're working with exponential functions and we want to solve for the exponent, then at some point we're going to be converting these to logs. So how many filters are needed to reduce the mass of pollutants to less than 150 grams? So we want to know what T is, the number of filters, if our M here is 150. So we have 150 is equal to 500 times 0.88 to the power of T. So to get it into exponential function, we need to have the base and the exponent on one side by itself. So we're going to divide both sides by 500. which will give us 0.3 equals 0.88 to the power of t. And now we can just change this, convert this to logarithmic form, because we have a number equals a base to an exponent. So we have log base 0.88 of 0.3 is equal to the exponent t. And using our change of base law, t is equal to log 0.3 divided by log 0.88, and that will equal 9.4. Okay. So now here's a little bit of a trick, because this breaks the rules of rounding, because we want to know how many filters are needed to reduce the mass of pollutants to less than 150 grams, less than 150. So we need at least 9.4 filters to get to 150. So if we rounded down to 9, we would have a value greater than 150. So we have to round this up to the next nearest filters, and this number of filters, and this would be 10 filters. Okay, so that's an exponential decay function. Let's move on to trying one that shows exponential growth. Okay, so this is example 2. It's just hidden in there. The number of students at a new college is currently growing at a rate of 4% per annum. Remember that per A means per year, or per annum, they mean the same thing. If the number of students continues to grow at this rate, it is projected that the college will reach its maximum capacity of 5,650 students in 4 years. So we want to determine the current number of students at the college to the nearest 10 students. So if we have an exponential function like this, y is equal to a times b to the power of x, then what these different variables here mean is y will be the number after t years. A is always the initial amount. And B will be the growth factor. I shouldn't say t years, I've got x there is the variable I'm using. So x years, so x is the number of years. So we have, it's going to reach its capacity. So that means this is y, and that would be x. So when x is 4, y is 5,650. We need to figure out what a is. This is what this is asking us, is to find a. What's the initial amount? So if our growth rate, if it's going at 4%, increasing at 4% per year, it's back to that thing like when you add GST to something that you're going to buy. The growth factor has to include the initial amount of students in there. So that means that our base is going to be 1.04, because we take that 4%, divide by 100, and then add it to 1. So we have a function that looks like this then. 5,650 is equal to a times 1.04 to the power of, it was 4 years, to the power of 4. And that's what we're solving for there. So this doesn't involve any logs. We just have to calculate numbers here. So we're going to have 5,650, and that's equal to a times 1.04 to the power of 4. Which is 1.04 to the power of 4 is 1.16986, let's say, rounding a little bit. So we want to solve for a, so we're just going to divide both sides by that. Now you could have also just divided both sides by 1.04, 1.04 to the power of 4. That works as well. Okay, so here we get a is equal to 4829.6, but we can't have 0.6 of a student, so we're going to round that up to 4830. That's what makes the most amount of sense. So now the next part of this example is a very common kind of question to see on the diploma exam, where you're given the way somebody has initially started to solve something, or the way they've carried through the solving, but they've made a mistake, and then it's up to you to determine what the mistake is. Usually something that's based on making a mistake with the exponent laws. So the governors of the college decide to expand the school by adding more buildings, which will increase the capacity to 8,000. Okay? So that would be our new y. In order to determine the number of years it would take before the college reached full capacity, one of the governors assumed the same growth rate and solved the equation 8,000 is equal to 4,830 times 1.04 to the power of n. So that makes sense, right? This is showing the initial amount that we determined in the previous part. This is the amount after n years. So we've changed from x to n. I should have been consistent and used n, but that's okay. And so his work is shown below. So what we want to see is what he's done here. So line 1 is correct. That one works. That's correct. And so then what he's done in line 2 is take the log of both sides. So again, that is correct. But if we look at line 3, what he's done is, although this exponent is only on the 1.04, this particular person chose to solve it by moving that n out in front of everything, which would imply that the exponent is on both the 4830 and the 1.04, and it's not. So this is where the mistake is. Okay, that's the mistake. So he used the power law incorrectly. Okay. So then what we need to do is we need to go from this line, or from line 2, and do this correctly, and then solve for it. So what we need to do here, because this exponent here is only on the end, but this is multiplication, we're going to use our product law. So we're going to write that as log 8,000 is equal to log 4830 plus n log 1.04. That is correct versus line 3 that is incorrect. And, so that's the correct use of the power law. So now what we need to do is just get all of our numbers on one side so that our n is on the other side. So we're going to subtract log 4830 from each side. So we get log 8,000 minus log 4830 is equal to n log 1.04. Then we'll divide both sides by log 1.04. So that can cancel. And we are left with n is equal to log 8,000 minus log 4830 divided by log 1.04. And you just have to make sure that you put that numerator in brackets. When you solve this, you should get approximately 12.9 years. Plugging that into your calculator. Okay, two rather specific types of exponential growth or exponential decay, which actually kind of come from science. Half-life comes from physics. So half-life, what half-life is it's the amount of time until half of a substance, a radioactive substance, so the amount of time until half of a radioactive substance is left. And different types of radioactive substances have different half-lives. Sometimes a half-life can be like 6 milliseconds. Like a very fast thing, it might be a couple of years. It might be a million years. There's many different types of radioactive materials, and they all have an individual and unique half-life. So the formula that we use for half-life looks like this. A is equal to A naught, that little subscript 0 is naught, times 0.5, right, for half, to the power of t divided by a capital H. And so first of all, this is not on your formula sheet, but notice that it is just an exponential function. The only thing that's different is our exponent is a fraction now. What everything means here, A is the amount left after a time t. A naught is the initial amount. 0.5 is the decay value, right? So that means half of it is left each time. T is the time, and H is the half-life. So the time, the initial amount, and the amount left after time t will vary, but for any single substance, the half-life will always be the same. And time, it doesn't have to specifically be in years, just your time and your half-life have to be in the same unit. Could be seconds, could be minutes, could be days, could be years, could be decades, as long as they're in the same unit. So example 3, we have in April 1986, the nuclear accident at Chernobyl contaminated the atmosphere with quantities of radioactive iodine-131. If the half-life of radioactive iodine-131 is 8.1 days, so that's H, determine the number of days, so we want to find our time, to the nearest day, that it took for the level of radiation to reduce from 100 units to 2 units. So reduce from, so that means our initial amount was 100 units, and our final amount, or amount after time t that we're going to find, is 2 units. I'm sorry, this should be a question mark beside time there, not number. So time is what we're looking for. So if we use our formula, or our sort of format for the formula for half-life to set this up, we have the amount remaining, the amount left after time t is 2, the initial amount is 100, the decay rate is 0.5, and we're going to raise that to the power of t divided by 8.1. Right? So the half-life is what goes in that denominator, that fraction. So I've seen diploma-like questions where they give you the equation, and it would look just like this, and then the question is, what is the half-life of the substance, which you can read directly from the equation if it's given like that. So the half-life here would be 8.1. And so then, of course, we're going to end up using logs to solve for this. So if we divide both sides by 100, then what we get here is 0.02 equals 0.5 to the power of t divided by 8.1. Converting to logarithmic form, we have log base 0.5 of 0.02 is equal to t divided by 8.1. And this is similar to the one we just did, except that we have it's equal to a fraction now instead of just a single number. So log 0.02 divided by log 0.5 is equal to t divided by 8.1. And you can do you can do this 2 different ways here. Basically, this is just cross multiplying and dividing. So 8.1 times log 0.02 is equal to log 0.5 times t. So t is equal to 8.1 times log 0.02 divided by log 0.5, which will give you a time period here of 45.7 days, and we want it to the nearest day, so 46 days. Right? Always round up there. Then the other type of exponential growth function that comes from science is what's called doubling time. It's similar to half-life. Half-life is the amount of time until half is left. Doubling time is how long it takes for this substance to double. So doubling time, it usually has to do with bacteria, or things that grow, which tends to be bacteria is what grows. So doubling time is the time taken for an exponential function to double. And the formula is quite similar to half-life. Again, it's A is equal to A naught, but this time our growth factor is 2, and then it's raised to the power of t divided by d. So A is still the amount after time t. A0, or A naught, is the initial amount. T is your time, and D is the doubling time. So exact same setup as half-life, except we use D instead of H, but I mean, you could put any variable in there that you wanted. So example 4, a patient feeling ill had a sample of bacteria taken from her throat. The sample contained 387 cells. Okay, so that is A naught. 24 hours later, So that's T. T is 24 hours. The sample was recounted and was found to contain 8,012 cells. So that's A. We want to find the doubling time. So now we're solving for the denominator of the fraction. So same calculations we did before, but our cross multiplying and dividing is going to look a little different. So we have 8,012 is equal to 387 times 2 to the power of 24 divided by D. So we'll divide both sides by 387. So we get 20.7028 is equal to 2 to the power of 24 divided by D. We will change to logarithmic form. Log base 2 of 20.7028 is equal to 24 divided by D. So log 20.7028 divided by log 2 equals 24 divided by D. We'll cross multiply and divide. So we have 24 times log 2 is equal to log 20.7028 times D. Divide both sides by log 20.7028. And so then D is equal to 24 times log 2 divided by log 20.7028, which gives us a doubling time of 5.489, or 5.5 to the nearest tenth, so 5.5 hours. Okay, and that's exponential growth and decay. And your assignment is a worksheet, and I think it's questions 1 to 12 on the worksheet that you can work on. And you've got the rest of the class to work on that. There's also the unit assignment that you can work on, although you will be given the entire class on Wednesday to complete that unit assignment.